Hello everyone, and welcome to the October 2025 episode of Astrochem Coffee. I'm your host, Brett McGuire, and on this month's episode, I chat with NRAO scientist Patrick Sheehan about what it's like to perform a data task so many times you eventually just develop an entire package dedicated to doing it that gets incorporated into observatory pipelines. Then later on, Jane Huang, an assistant professor at Columbia University, sits down with me to talk about how she got into astrochemistry and what's driving her research today. Finally, in the Percolator, we take a look back at the discovery of the cosmic microwave background, one of the most important observational breakthroughs that provides evidence for the Big Bang. All that in addition to our usual grab-and-go papers and chalkboard announcements. But first, let me tell you that today's Cup of Joe is from Becky's Diner in Portland, Maine. You know you're either in a tourist trap or somewhere special if the breakfast diner you've arrived at hands you a pager when you show up to wait for your table. In Becky's case, the number of locals there was a good indication that this was the real deal, which was confirmed when, upon entry, we were greeted by a good old-fashioned pie case filled with the day's offerings. Their coffee is actually a little too fancy for my taste, but it paired really well with the special of the day, cinnamon swirl pancakes. You could literally see the swirl in them. I didn't even need maple syrup. It was wild. Also, one last thing before we go on, we used to post updates and such to our Twitter account before, Twitter ceased to be Twitter. We've started up a new account over on Blue Sky. You can follow the show there now to get updates and announcements. We'll also be trying to post new astrochemistry relevant articles as we spot them in the literature on a regular basis in between our monthly episode drops. So you can find us at astrochemcoffee.bsky.social. We'll have a link in the show notes on the webpage as well. Let us know if you have ideas for other things you'd like to see going on this account. This last month, I was in Portland for a workshop on astrochemistry in the broadband era, looking particularly at the wideband sensitivity upgrade that's coming online soon for ALMA, and even further ahead for the next generation Very Large Array. One of the keynote speakers there was Patrick Sheehan, who was giving a talk to prime the audience for discussions on what it takes to generate new software to reliably automate the tasks necessary to reduce huge volumes of data. We sat down to chat about his own experiences in this area during one of the coffee breaks. I started off by asking Patrick to tell us a little bit about his role at NRAO.
So I am a scientist at NRAO, so my role is about 75% of my time goes to functional work, with a little bit of the rest devoted to science. And I spend a lot of my time thinking about ways to deliver data to science PIs that is as high a quality and ready to use as possible. So initially that was spent developing a lot of these automated self-calibration tools that I guess we'll talk about. But now has sort of morphed into ALMA pipeline work, and I'm also involved with the CASA team as well, maintaining and developing features for CASA.
Cool. So we're at this workshop, and what really struck me during your talk was you said in the development of this, what sparked your idea to make this into a pipeline was that you did it 300 times by hand, right?
And I should add that I did it probably like 80 times, and John did it like 220 times.
Fair enough.
And I tried to keep up.
Fair enough. Yeah. So let's start off with what is the science that you're interested in, that you're working on then, and how did self-calibration help? As part of that, what is self-calibration and why was it so useful to the science you were trying to accomplish?
Right. So we were working on this survey of protostars in Orion, protoplanetary disks in Orion, really, with the goal of trying to measure what their properties are, their masses, their radii, etc., to have an idea of sort of what the demographics of the population of young disks are, because that has a lot of important information for how planets form, etc. And the reason we needed self-calibration is because ALMA has this regular calibration process, right? You go back and forth between observing a calibrator source and your target source. And your target source is never going to be looking through the exact same atmosphere at the exact same time as your calibrator. And so there can be residual corrections, the calibrations that are needed to get the best possible calibration. And so the idea of self-calibration almost sort of sounds like magic, but the idea is basically that because we have enough antennas and enough baselines and enough constraints, you can actually use your own science target to get an idea of what the atmosphere is actually doing at the same time and at the same position as your source, and use that to correct itself for those residual calibration issues. And you really need that because you want to make sure, if your data is not calibrated properly, it can lead to getting incorrect source properties, essentially.
Sure, absolutely. So what is challenging about self-calibration?
Self-calibration itself isn't all that hard, right? It's a very straightforward recipe, right? You make an image of your source that provides the model. You put that model into GainCal and it gives you some solutions, or your Gain Calibrator and it gives you some solutions. You apply those, you make another image, and you see did things get better or not. What's really difficult, I think, is doing that in an automated way, because you have to figure out, it's like I said, very easy to write down that recipe, but how do you have to think about what decisions you are internally making when you're saying, oh yes, that image looks better, or this is why I'm choosing to calibrate on this time scale or with this set of antennas, etc. You need to think about why you're making those choices, and then once you've done that, you need to make sure those heuristics work not just for your one data set, right? It's 300 sources, it sounds like a lot, but they were all taken in a very uniform way. But there's people out there that are doing very different science that want this capability as well, and you need to make sure those heuristics are going to work for all of the sources that you might use this on.
Yeah, so I was going to ask, right? So you're working on disks in this case, right? So I could imagine that you can look at an iteration with your eyes and say, oh yeah, that disk structure looks better. The negative voles went away, or I can see this feature sharper or whatever. You can also imagine that disks have some sort of fiducial, well-known structure, and so you can make some automated heuristics to look at that and say, did it improve or not? So you don't have to use your eyes. But how do you translate the work that you did there onto folks that are observing external galaxies, or folks that are observing star-forming regions, right? Which have very different structures and very different properties, at least in my mind, right? How do you develop heuristics for that?
Yeah, so I think when we sat down and thought about what it was that really constituted an improvement in an image that is relatively source agnostic, right? These residual calibration errors are going to end up leading to the flux in your image being sort of dispersed throughout the image. So you're going to, at some level, see some decrease in the peak, right? If everything is lined up properly, it all adds together and you get a bigger peak. If you start to add some decoherence, it shifts things a little bit, and they don't all add up constructively anymore. And then the other aspect of this is also that tends to disperse add more noise to the rest of your image because you're moving your flux around to the rest of it. And so that kind of led to two relatively straightforward heuristics that we ended up using, which are looking at, does the signal-to-noise ratio increase? Because if you are correcting those errors, you should get things to add more constructively together. And then by the same token, the noise that you're adding to your image as it's getting added actually to the source where it should be, that tends to decrease the noise in the image. So those two things seem to be fairly universal properties. Of course, there's a lot of tricks that then go into figuring out how to properly measure. Peak flux isn't all that hard, but to measure what the noise is in your image, because a galaxy looks very different in an image, like you said. And so that's where. And part of the reason this didn't all happen earlier, I think, is because historically, when you're making an image, you need to put some sort of mask down to guide where the emission is. And it was only really not long before we did this that automatic masking was developed, which, with a relatively limited range of parameters that you need to tune, that you pretty much automatically mask a galaxy, mask a protoplanetary disk with the same set of code.
Very cool, very cool. Okay, so 2 final questions. One, correct me if I'm wrong, but users can now take advantage of this on basically any data set in the archive, right, through this Audi tool. Is that correct?
Yep. So Audi, you can more or less any Alma data in the archive you can go in and ask it to generate an image with a certain set of characteristics, and it will retrieve the regular calibration data and it will rerun self-calibration with whatever the latest version is, and then ultimately use that self-calibrated data to produce your image.
Very cool. And this is a tool that's available only through the NRAO entry or mirror of the archive, is that right?
It's through the NRAO data archive, so data.nrao.edu. The Alma archive does hold pipeline. The Alma pipeline will run these self-calibration routines as it's taking data, and those
going forward.
Those will going forward. So everything from cycle 10 onwards has had, at some level, single fields initially, now mosaics in cycle 12 as well, have had automated self-calibration, and it will run. So the pipeline run will include that, and those products get ingested into the Alma archive.
Okay.
But if there are improvements, a cycle 10 mosaic won't have that product in the Alma archive. So if you go to the NRAO archive, which is a separate entity, the data.nrao.edu, you actually have the ability to pick a data set. It will rerun the self-calibration using the most recent version of the pipeline, and then spit out those products for you.
And that includes, in theory, anything even before cycle 10?
It should, yes,
okay.
as long as it's works with the current pipeline.
Okay, very cool. Okay, so the last question is, you went through all of this work, you self-called 80 or 300 sources vary, individual disks. What was the coolest science result that got you the most excited out of all of that work?
So I think something that we weren't entirely expecting is when we were doing this, it was still early on in the substructure era, and we didn't necessarily know. We knew we'd had like D# and we'd had HL tau, and so we knew that older disks were starting to show lots of signs of substructure, but we still didn't really know for these young disks that are less than 1 million years old whether there was any sign of substructure or not. And so I think this was really, there were a couple of one-off observations that had seen this, but this was the first time we actually got a sample, because there were so many disks looked at with high enough angular resolution. We actually got a sample of disks, the first sample of young disks that actually showed substructures in them. I think we're still 8 years later, the jury's out on what that substructure means, but I think it was something I was excited about and hadn't been expecting to see when I went in.
Very cool. All right. Well, thanks for taking the time to chat with us.
Yeah, absolutely. Thanks for having me.
And now, a word from our sponsors. November's here, the month when we all pretend to eat salad before immediately housing 3 pounds of mashed potatoes and gravy while giving a dubious side eye to the cranberry jelly that has held the shape of a can disturbingly accurately throughout the entire meal. The problem? Food comas. So sleepy. Luckily, Starducks has everyone covered with their new Thankful Sips collection. Whether it's the pecan pie latte, the cranberry cold foam, or the inexplicably popular stuffing spice macchiato, Starducks knows how to keep those holiday vibes percolating. So grab a cup, count your blessings, and maybe be thankful that this year, the only thing getting roasted is the coffee beans, not your cousin's opinions over dinner. This is the grab and go, because sometimes you just can't do more than skim the menu. We've got rapid fire overviews of 10 fantastic papers from this month's Astrochemical Literature for you as usual. Starting off with number 1, Molecular Mobility of Extraterrestrial Ices, Surface Diffusion in Astrochemistry and Planetary Science, by Ligterink et al. On the archive to appear in PCCP. This paper focuses on surface diffusion, how atoms and molecules move across ice mantles as a key process shaping interstellar and planetary chemistry. The authors review experimental, theoretical, and computational approaches to measure diffusion barriers, covering simple species like hydrogen and oxygen atoms as well as complex molecules. They highlight how mobility depends strongly on ice structure, composition, and temperature, with amorphous versus crystalline forms yielding different reaction efficiencies. Diffusion controls not only reaction rates in molecular clouds and protoplanetary disks, but also volatile redistribution in comets and icy moons. The review emphasizes the need for better laboratory data under astrophysical conditions to constrain models of ice chemistry, volatile transport, and ultimately the chemical inheritance of planetary systems. Number 2, a quest for sulfur-bearing refractory species, identification of CAS in the interstellar medium, by Tassa Chevelli et al. On the archive to appear in AppJ Letters. Sulfur depletion in dense clouds suggests much of the element is locked in refractory materials. This study reports the first identification of calcium sulfide, CaS, in the interstellar medium, detected via ALMA observations toward G351.77 minus 0.54. They cover 4 lines of CaS, and they base their identification on one which appears to be unblended, and a good match to CaS laboratory data. They also claim tentative detections of Ks, potassium sulfide, and KSH. Their derived abundances are about 3 orders of magnitude below those of abundant sulfur-bearing species like SO2, CH3SH, and SIS in the source, leading them to conclude these new species are not a large reservoir of sulfur. Number 3, extended and compact ortho H2D+ structures close to the moment of star formation. Evidence from ALMA ACA observations in Taurus, by Tokuda et al. In AppJ. The authors here present ALMA ACA observations of ortho H2D+ in 3 sources in Taurus: L1544, a dense prestellar core; MC35MM, a candidate for a first hydrostatic core; and MC27, which hosts an embedded Class 0 protostar. Extended emission is detected in all 3 sources using the single-dish total power data, but compact emission was only found toward MC35MM, and there it was relatively low significance. They suggest this implies that while ortho H2D+ may be widespread at extended scales, it is rapidly converted into more highly deuterated molecules in the more compact high-density regions. And this could potentially make it a good tracer of a very narrow span of time just before or after star formation, where it is compact but has not yet had time to deplete. Number 4, methanol emission tracing ice chemistry and dust evolution in the TW Hydra protoplanetary disk, by Eiley et al. On the archive to appear in AJ. This paper presents new, high-sensitivity detections of methanol emission in TW Hydra using ALMA, along with modeling to connect gas phase methanol chemistry to ice chemistry and dust evolution. They detect 4 individual transitions of methanol in the disk, the only solar-type disk where methanol has so far been observed, and map its radial extent. They find it to be centrally compact, and the detectable abundances fall off somewhere between 50 and 100 AU, depending on the exact transition. While there are some hints of substructure, nothing is really resolvable at the resolution of the observations. At least the substructure would be about on the same size scale as the beam itself. Chemical models make it clear that photodesorption is a key process to releasing methanol from the ice mantles in this source. But even including this with several other processes, they cannot reproduce the observed gas phase abundances, and this suggests that additional processes like vertical mixing and radial drift might be required to explain the distribution of methanol that they see. Continuing on the theme of methanol, we have number 5, observation of 17-OH methanol and 18-OH methanol in Orion KL, a new tool to study star formation history, by Watanabe et al. On the archive to appear in A&A. In this study, the authors use ALMA data to map these species across Orion KL and determine isotopic ratios. They derive ratios that seem to be broadly in line with local ISM values, but they also compare them to those derived for CO and methylformate, mostly from literature sources, and they discuss potential reasons why these values may differ. They do differ in some circumstances, and they don't in others. One of the big processes that they put forward here is selective photodissociation, particularly in the case of why low J transitions of CO may present different isotopic ratios than high J transitions of CO. They suggest that future observations of the two isotopologues, the 17OH and 18OH in methanol, should take place in disks where the radiation field is well characterized, and that this could help determine the role of selective photodissociation in particular. Number 6, vibrational spectroscopy of C60+ and C70+ in the mid-infrared, a comparison with astronomical observations, by Douglas Walker et al. In APJ. Laboratory gas phase infrared spectra of both C60+ and C70+ are reported here using helium tagging spectroscopy. The study refines previous measurements of C60+ and extends coverage to the 6 to 9 micron region. The authors find strong absorptions near 7 microns for both cations, with widths reflecting short complex lifetimes. Comparison with theoretical models show that C60+ spectra agree reasonably well with DFT predictions, but C70+ deviates substantially, with the harmonic approximations apparently being insufficient. The authors suggest that these spectra may help explain astronomical mid-infrared features near 7 microns that have been observed in planetary nebulae, and they also say that the emission there could therefore arise from mixtures of neutral and ionized fullerenes like C60 and C70+. Number 7, we got a twofer. 2 papers for the price of 1. The first one is mapping CO ice in a star-forming filament in the 3 kiloparsec arm with JWST. That's by Gramsci et al. On the archive to appear in the Open Journal of Astrophysics. And the second one is the colors of ices, measuring ice column density through photometry. This one's by Ginsberg et al. On the archive, again to appear in the Open Journal of Astrophysics. In these 2 papers, the authors map ice absorption toward the galactic center using JWST narrowband photometry. One of the mapped clouds is in front of the galactic center, not within, and likely lies in the poorly understood 3 kiloparsec arm of the inner galaxy. Comparing CO ice column density to extinction, they infer CO ice abundances that exceed the total CO gas plus ice abundance under solar neighborhood conditions, leading to the inference that the total CO, and in turn the total carbon, is higher in these clouds. They propose that CO ice can be used as a tracer of total metallicity. The analysis is based on laboratory ice measurements, and they present a summary of which JWST filters are likely to exhibit detectable ice absorption. Number 8, the survival of aromatic molecules in protoplanetary disks by Piacentino et al. On the archive. This study examines whether small aromatic molecules can survive the intense UV and X-ray radiation of protoplanetary disks. Using laboratory photochemistry, theoretical modeling, and disk simulations, the authors assess the photostability of benzene and similar substituted benzene species embedded in ices or bound to grains. They find that aromatic rings are more robust when shielded by ice mantles or clustered within refractory material, but readily fragment in the gas phase, which would be near the disk surface. Interestingly, they find that substituted benzenes do not have any significant change in survivability. They suggest that the survivability is dominated by the delocalized pi electron system in the core benzene ring, and it's really not affected by what's attached to the ring. Survival thus depends strongly on local extinction and disk geometry, what ices are present, and how much radiation is getting to those ices. The results also suggest that aromatic precursors of PAHs and prebiotic molecules may persist in the midplane, where they are shielded by their incorporation into ices, and thus be incorporated into planetesimals. Number 9, glycolaldehyde and ethanol toward the L1157 outflow, resolved images and constraints on glycolaldehyde formation, by Robucci et al. On the archive to appear in A and A. The study used NOEMA to image glycolaldehyde and ethanol in the L1157 outflow, with both molecules being detected. The authors modeled the chemistry after the shocks, testing whether glycolaldehyde might be forming in the gas phase from ethanol, as has been recently suggested in the literature, or whether it's coming entirely from grain surface processes. Now, ethanol doesn't have known gas phase processes, so it's assumed to be ejected directly from the ices, and then gradually consumed in the gas phase to make glycolaldehyde. And overall, the data seem to rule out the idea that glycolaldehyde could be coming entirely from grains, and that suggests that gas phase reactions, fed by ethanol released in these shocks, may play a major role in its formation, at least in this source. Finally, number 10, chemical modeling of aminoketene, ethanolamine, and glycine production in interstellar ices, by Willis et al. On the Archive, to appear in A&A. The authors here combine laboratory data and chemical kinetics to simulate atom addition and radical-radical reactions involving CO, ammonia, and CH2 species under cold conditions. They find that aminoketene is formed by non-diffusive reactions, and that ethanolamine and glycine can then form via sequential hydrogenation and addition reactions to that aminoketene on those grain surfaces, and that the yields are sensitive to the UV-driven radical production. They also examine the survivability of these species in the gas phase and whether it is likely to differ between shocked regions, where they have been non-thermally liberated from the ices, and hot cores, where they have been thermally liberated from the ices. They find that the molecules have a much higher survivability in the shocked regions, and this may help explain why so many complex molecules are found in the shocked molecular cloud G plus 0.693 minus 0.027 that are otherwise not seen in molecule-rich hot core sources. And that's your grab and go for the month. We can, of course, only juggle so many cups. For a more complete list of papers, we recommend checking out the amazing lists maintained by David Woon at the astrochemist.org, as well as subscribing to the Astrochemical newsletter. You can find links to these websites, as well as each of the papers in this month's grab and go, on our website at coffee.astrochem.net. And if you have a paper you think we should include in next month's edition, you can do as Adam Ginsberg did and shoot us an email with a link to the paper and a 4 to 6 sentence summary at coffee@astrochem.net, and we'll be happy to feature it in the grab and go. And now, a word from our sponsors. This month we're also sponsored by Over-Engineered Solutions, Inc., who want to introduce you to the GobbleStopper, the revolutionary kitchen gadget that finally answers the age-old question, why is the turkey still frozen? Using cutting-edge thermologic turboblast technology, the GobbleStopper can thaw, baste, and emotionally support your Uncle George, all in record time. It's like having a sous chef who doesn't judge your life choices, or your cranberry sauce from a can. So this Thanksgiving, skip the stress, embrace the science, and let the GobbleStopper turn your panic into poultry perfection. Because nothing says gratitude like a turkey that actually cooks on time. While I was at that same workshop in Portland, I also had a chance to sit down with one of our invited speakers, Jane Huang, to talk about her path to working in astrochemistry. Well, thanks for chatting with us, Jane. So what I wanted to start off and ask you is, how did you get interested in astrochemistry to begin with?
Well, so when I started college, I wasn't exactly sure what I wanted to do. There were a few different things I was interested in. I was taking physics classes. I wanted to take chemistry classes. I started working with this astronomy professor over the summer on extragalactic astronomy. Nothing to do, strictly speaking, with astrochemistry, but I was really interested in astronomical spectroscopy because I thought it was just really cool that you can just look at how much light something is getting at different wavelengths and figure out, like a detective, what you are seeing.
Yeah.
And then I learned about something called diffuse interstellar bands. And I just thought it was wild that there was like all this chemistry happening in space that's really different from the chemistry that we're used to in everyday life. Because you're taught all these rules in high school, and then the astronomers tell you you need to forget about those rules.
Absolutely, yeah.
So then in my senior year, I started working with an astrochemist, Takeshi Oka, probably most famous for his work on H3+.
Which violates those rules we were taught.
Exactly. H3 plus is a molecular ion, and certainly something you never learn about in high school chemistry.
No.
So I thought it was really interesting what he did, and so I wanted to continue studying astrochemistry in grad school. And so, at the time there weren't that many astrochemists working at the faculty level in the US, so that led to a very short list of people that I reached out to talk to about whether they were taking students, what kinds of projects that were possible to work on in a PhD. And one thing I kept hearing over and over again is, ALMA is the future. ALMA is the future. So ALMA was a radio telescope that was constructed shortly before I started grad school. Most powerful radio telescope in the world. And one of the big things that it was designed to do was to study the chemistry of what are called protoplanetary disks. So these are the disks of gas, dust, and ice around young stars. So I went to do my PhD at Harvard, which is one of the foremost centers for protoplanetary disk studies. And so there I was studying both the physical structure of protoplanetary disks and their composition using ALMA.
Very cool. So, correct me if I'm wrong, but Harvard is a unique environment because you have a mix of faculty from the actual astronomy and chemistry departments, but also permanent research staff at the CFA, the Center for Astrophysics, right? And so that seems a little different from the structure that a lot of folks think of when they go to graduate school, where they're just working with one PI. So did you get to interact with the research staff? How do they influence the way that you did your research, if at all? You tell us a little bit about that environment.
Yeah, so you're right that it's a very unique environment. In fact, the astronomers at Harvard are outnumbered by the astronomers at the Smithsonian Astrophysical Observatory. So we had something called a disk group, which was led by a mixture of Harvard and Smithsonian people, and I feel fortunate that I was able to be able to learn from the expertise of so many different people. So the CFA is so big that it's impossible to know everyone. It's like years later, I will meet people who are at the CFA at the same time as me, and we never spoke to each other and even necessarily knew each other existed. But then the advantage of being at some place so big is that it feels like there's an expert in almost any aspect of astronomy that you would want to be able to ask about.
That seems, it seems like a great thing when you're working on what is increasingly mandatory interdisciplinary science, right? Especially when you get into things at scales that protoplanetary disks sort of bridge from clouds all the way down to planets, right?
Right.
It's an interesting mix. Mm-hmm. Yeah. Okay, so PhD in protoplanetary disks. Presumably you kept working on that in your postdoc?
Yes, I did. So then I moved on to University of Michigan, which is another focal point of protoplanetary disk research in the US. And so I continued doing things with ALMA, but then started branching out more, collaborating with people working at other wavelengths, working with telescopes such as VLT Sphere. And then at Michigan, I started thinking more about the environmental context of protoplanetary disks. They're not just these islands of planet formation, but they're affected by their surroundings.
Very cool. So that's, you're talking about, and correct me if I'm wrong, but you showed images where you have material falling onto the disk from its surrounding cloud, and trying to look at the way that the initial cloud conditions affect the eventual composition of the disk, or something else than that?
Well, not necessarily the initial cloud conditions, but just the fact that there's external material seemingly being transferred to disks.
I see.
Another aspect that I've been looking at recently is how disks are affected by radiation from nearby massive stars.
Okay, cool. So we talked a few podcasts ago about how the surfaces of protoplanetary disks actually are kind of like a PDR, a photon-dominated region, because of the radiation from the central star. But in your case, your disks are almost like super PDRs because they're being blasted not just by the central star, but by the surrounding additional protostars.
To be determined. So
Okay.
for those disks so far, I've only looked at dust continuum, which is just telling us what the solids are doing in the disk midplane, the dense region that's more protected from radiation.
Okay.
But we're getting new ALMA and JWST observations to look at the gas. So that being said, the disks I'm looking at are not as extreme as some of the other disks that people have looked at. So there have been published studies over the last couple of years of a couple of disks in the Orion star forming region where they do see these molecules that you would only expect if you have these really high levels of ultraviolet radiation. So, and the open question is, well, how commonly should we see these across different kinds of disk environments?
Yeah, that's an interesting question. So this is presumably where you're taking your research group now, because you're faculty at Columbia and have been for 5 years?
No, a little bit over 2.
A little bit over 2. Wow, okay, time flies.
Or doesn't.
Well, it depends. Okay, so a little over 2 years then. So is this how the sort of questions that you're building up your research group to try to tackle? Do you have different areas of investigation you're also looking at?
Yeah, I mean, I would say that my big focus in the near future is going to be on disk environments, but the other aspect that I've been thinking about also is how disks change with age, and that intersection with those environmental effects, because the environments are also not constant with time.
Yeah, that's a great point. So I guess naively, we think about planet formation in stages where you start with a cloud, it collapses to a core, then a disk forms, but it's still embedded in its cloud. And then the cloud starts to dissipate at some point surrounding the disk, right? And this is, you're trying to tie that timeline to cloud change and dissipation and the cessation of accretion or changing the amount of accretion onto the disk to observable properties and figuring out what it's going to do as the disk evolves?
Yeah, basically. I mean, one of the things that we still don't know for sure is when exactly does planet formation start.
Oh, okay.
And so we know that that the disk environment is changing. Like you said, the disk is, there has tons of material falling onto it, and then eventually it'll dissipate. And then from the radiation side, disks are moving around in a cluster. They're not just always parked at the same location relative to the star. So we need to understand, when does planet formation start and how long does that take place, and how does that compare to all the other external processes going on?
Very cool. Okay, I have probably a naive question, but I hadn't considered the fact that the disk system itself will move relative to some of the other, say, massive stars in the region. Does it move enough in the lifetime of the disk to change like the irradiation angle onto the disk itself?
So that's one of the questions that's one of the open questions. I mean, there's something called the propelid problem, so propelids are like these disks where you can see in the images there's material being blasted away. It's a propelid lifetime problem. And if you measure how much mass they're losing, it seems like the propelids shouldn't live for very long, but you're seeing them at an age of around 1 million years, maybe a couple million years. And so there have been different ideas for why that could happen, and one of them could just be that the irradiation levels have changed enough over time that we're happening to catch them when they're losing a lot of mass, but maybe at other times in their life they're better shielded from the radiation for different reasons.
Okay, a variable mass loss rate. Interesting. All right, so one last question for you. What do you think is the most exciting discovery you think might happen the next, say, 5 to 10 years as we're here at the ALMA WSU and NGVLA conference, as these capabilities start coming online? What do you think new frontiers are going to be opened in research for protoplanetary disks?
Well, so to some extent, this has already been done a bit, like the surface has been scratched, which is studying something called circumplanetary disks. So protoplanetary disks, despite what the name sounds like, are the disks around young stars. And with astronomy, sometimes it's turtles all the way down. So the young planets also can have little disks around them. Now, there's been one detected for sure, and some candidates, and then some analogs around brown dwarfs, other substellar objects. There was a recent study, I think, looking at using JWST to study the disk around a substellar companion. And I think with the better resolution sensitivity of future instruments, it would be interesting to know, like, what are these circumplanetary disks' physical and chemical properties in much better detail than we have now.
Awesome. Is it, again, a possibly naive question, would you expect that it's possible that you would observe one of these circumplanetary disks and find that its composition varies dramatically from the ring, the radius, material in the radius that it occupies in the protoplanetary disk?
So if I remember correctly, the recent study of the substellar companion disk basically did find that. But of course, there's no guarantee that system formed in the same way as the less massive objects. Okay. So we expect that the formation process should also impact the disk composition. But that in and of itself would be an interesting result.
Really cool. Would that be a way to track potential migration of these planets as they move from one location to the other, or not?
I think the naive answer is yes, but then the sort of always more cautious answer is it depends.
Fair enough, fair enough. All right, well, thanks so much for taking the time to chat with us today.
Okay, well, thank you for having me on.
Well, folks, one of the Dougs managed to stick a fork in our toaster while it was still on. They're fine, but that toaster has never been the same since. It is constantly emitting an almost imperceptible buzzing noise. Either that or we all now have tinnitus. In any case, it's sitting right next to the percolator, which seems to be dropping not so subtle hints that it's also experiencing the background buzz, as we've been getting non-stop newspaper clippings from the 1960s about Penzias and Wilson. A while back, Green Bank Observatory went through a rebranding, complete with new logos, color schemes, and a sort of catchphrase you can see written all over the place. The universe is whispering to us. Now, they certainly mean this in a broader sense, but it's especially true as it applies to what the percolator's been kicking up today, the discovery of the cosmic microwave background, or the CMB. The CMB is ancient light left over from the Big Bang. Shortly, on a cosmic scale after the Big Bang, the universe cooled enough for light to travel freely. This is light that we are now observing today as the CMB. The CMB is strongest in the radio at low frequencies because the light from early on in the universe has been dramatically stretched as the universe expanded over billions of years. It's been redshifted. The visible and ultraviolet light emitted in the early universe has been shifted all the way into the microwave portion of the spectrum by the time it has reached us today. One of the most striking features of the CMB is its remarkable uniformity. It appears essentially the same brightness when observed from any direction in space. It's coming from all around us. This isotropy tells us that the early universe was extraordinarily homogeneous. On the other hand, extremely precise measurements have revealed tiny fluctuations, and these minuscule variations are crucial because they are thought to represent the seeds from which galaxies and stars ultimately grew. The story of the detection of the CMB starts at Bell Telephone Laboratories. See, back in the day, they did a ton of actual scientific research and actually contributed quite a bit to advancing astrochemistry as a discipline. When the Bell telephone monopoly was broken up in the 1980s, back when we actually broke up monopolies instead of encouraging them, that lab became part of AT&T, which basically demolished its budget and virtually all research stopped. But in the 1960s, they had a headquarters in Murray Hill, New Jersey, where a pair of researchers, Arno Penzias and Robert Wilson, were working on technology for communicating with the recently launched Telstar satellites. They were using an antenna perched atop Crawford Hill in Holmdel, New Jersey, and were trying to isolate, identify, and compensate for every source of noise in their signals.
In the research at Holmdel, it was evident that some of the noise came from the system, some came from the warm envelope of air around the Earth, and a negligible amount came from the Milky Way galaxy and other galaxies. Yet, there was always an unexplained residue.
This was from Walter Sullivan of the New York Times News Service, as reported in the Sunday, May 23, 1965 edition of the Oregonian.
Working on the Telstar frequency of 4,000 megacycles, they still were unable to eliminate the leftover noise. They took the huge antenna apart, machined its moving parts, and subjected its electronic circuits to scrutiny comparable to that used in preparing a manned spacecraft. Perhaps, they thought, radio emissions were leaking into the antenna from behind it. Hence, they carted a transmitter around nearby fields, testing to see if its emissions entered the system. They did not. Finally, they reassembled the whole contraption and found the emissions were still there.
Now, a report in 1978 in the Abilene Reporter News would later recount that
they had even investigated the possibility that the signals represented excessive heat in their antenna, caused by pigeon droppings.
Now, after accounting for every other source of noise, though, they were left with something the equivalent of what a black body would emit at a temperature of about 3.5 Kelvin, so 3.5 degrees above absolute zero. It was constant and didn't vary with time of day or the inclination of the receiver. It came from everywhere.
The only explanation which so far seems to fit the data is that the telescopes are receiving signals generated by the primordial fireball, or the Big Bang.
This is what Arthur Hill of the Houston Chronicle wrote in a Sunday, January 30th, 1966 column. As it turns out, a group at Princeton, led by Robert Dicke, had almost simultaneously predicted that if the Big Bang were indeed true, and mind you, this was still a contested theory at the time, we should indeed see some of its leftover light. They suggested it would resemble a black body at 10 degrees Kelvin, remarkably close to the measurement made by Penzias and Wilson. As it turns out, this actually was not the first reported measurement of the CMB. You may remember way back in episode 3 in 2023, we talked about the very first molecule seen in space in 1937. One of the individuals responsible for that was Andrew McKellar of the Dominion Astrophysical Observatory in Victoria, British Columbia, in Canada. In 1971, he wrote a paper in the Publications of the Dominion Astrophysical Observatory titled
Molecular Lines from the Lowest States of Diatomic Molecules Composed of Atoms Probably Present in Interstellar Space.
Now, it's important to note the probably. Remember, it was still a matter of intense debate, even 4 years after the original detections of these molecules, whether or not molecules existed in space at all. But in the abstract of his paper, he's summarizing some of his thoughts and other people's works concerning the spectra that had been taken by atoms of, atoms here being a person, ADAMS, of molecular line absorption toward a number of different sources in interstellar space.
The results of atoms showing that only the lowest and next higher rotational states of CN are sufficiently populated to give interstellar lines are of particular interest. They allow the determination of a rotational temperature for the region where the CN absorption takes place.
In other words, something was causing the CN to be more excited than it was supposed to be, and by knowledge of the energy levels of CN, the black body temperature of that thing could be calculated, and a value of 2.3 Kelvin was arrived at. We now know that indeed it is the CMB that is driving these processes, but at the time, McKellar and others did not recognize it for what it was. And they can hardly be blamed. The Big Bang itself had only been proposed a few years earlier by Lemaitre, and it was not yet widely accepted. And indeed, the idea that we should see a CMB at all if the Big Bang was true was not proposed until 1965 by Dicke's group at Princeton. In the end, Penzias and Wilson would win the Nobel Prize for Physics in 1978, just 13 years after their discovery. In describing that discovery, Bell Labs said,
"It was a fundamental breakthrough in understanding the origin of the universe."
It was, in fact, not pigeon poop. Taking a look at the chalkboard in job news, there is an opening for a PhD student at the University of Valladolid in Spain to work with Amanda Stieber on rotational spectroscopy for astrochemical applications, as well as combustion chemistry applications. The deadline to apply is November 21st, so you still have a couple of weeks here. In the course of the PhD work, the candidate will use microwave spectroscopy and electrical discharge sources to investigate the chemical reactions that produce astrochemically relevant molecules. The results will be used to look for new and novel species in the interstellar medium through collaborations with astronomers, while at the same time being used to improve astrochemical models. The individual will also have a chance to investigate combustion reactions and be involved in the instrument development. We'll have contact info for Amanda on our website. In conference news, there is a conference exploring the aromatic universe in the JWST era to be held July 6th to the 10th in Ontario. The symposium will bring together experts from observational astronomy, laboratory astrophysics, theoretical modeling, and quantum chemistry to explore the latest discoveries and future frontiers in PAH and fullerene research. With a special emphasis on extragalactic PAH studies, participants will discuss how new observational capabilities like JWST and SphereX, as well as cutting-edge theoretical and experimental approaches, can expand our understanding of these key interstellar species. They have a link to sign up for news alerts there, sort of pre-registration or expression of interest on the website, so go ahead and check it out. There's also going to be a session, The Icy Universe Revealed by JWST, sponsored by the American Chemical Society Astrochemistry Subdivision at its spring meeting in Atlanta, Georgia, to be held March 22 to 26th. Abstract submission is already passed, but registration is open for some time. There will be many astrochemistry sessions at the International Symposium on Molecular Spectroscopy in June, the 22nd to the 26th, to be held at the University of Illinois in Champaign-Urbana. Abstract submission for this will open in February with a deadline at the beginning of March. There's going to be a session at CoSPAR 2026 entitled Interstellar Chemistry, Interstellar Origins, Observations, Experiments, Models, and Theory of the Molecular Evolution of the Universe. CoSPAR will be held August 1st to the 9th in Florence, Italy. It also looks like the 2026 European Conference on Laboratory Astrophysics is going to be held the 21st to the 25th of September in Heidelberg. And finally, we have a save the date for Cosmic Rays 4, the Salt of the Star Formation Recipe, October 5th to the 9th in Pisa, Italy. Finally, we're going to remind you that there's a special issue in the journal Icarus on carbon in planetary environments, sources, and evolution. This special issue is intended to present new research from laboratory experiments, modeling work, data analysis, and other scientific techniques on carbon in planetary systems and beyond, including astronomical sources. Submissions are open to anybody, and they are due by the end of the month, November 30th. And that's it for this month's Astrochem Coffee. Once again, you can find links to all the papers and meetings from today's episode on our website, coffee.astrochem.net. And if you have ideas for the grab and go or double shot, general thoughts or comments, you can always get in touch with us at coffee@astrochem.net. Don't forget, you can now follow the show on Blue Sky at astrochemcoffee.bsky.social. Special thanks as usual today to ChatGPT for its writing assistance. And until next time, stay safe and keep your head in the molecular clouds.